What if I told you there's a ring out in space, and it's so big it would take 15 full moons just to cover its diameter?
Whoa, that's huge. Sounds like we're talking like cosmic scales huge.
Exactly. And that's what we're going to be diving into today, this recent discovery that's kind of shaking up, well, how we understand the universe. You know, a lot of you have been asking us to look into the mysteries of these ultra-large structures out there. And this one is, well, a doozy.
Yeah, these ultra large structures are always so fascinating. They make us rethink how the universe is organized.
Exactly. And this one, they're calling it the Big Ring. It really takes the cake. We've got a research paper here and a press release, too, from UCLan, the University of Central Lancashire. They're the ones behind this discovery.
Euclid, okay.
Yeah, I was a PhD student there, Alexia Lopez, who led the research. And the paper itself, it was just published in, let me see, the Journal of Cosmology and Astroparticle Physics.
So cutting edge stuff then.
Oh, absolutely. So back to this big ring. It's located, get this, 9.2 billion light years away. And they think its diameter is something like 1.3 billion light years.
Yeah.
I mean, to even try to picture that, it's like if you were traveling around the circumference, it would take you 4 billion light years.
Yeah, those are numbers that are hard to even to wrap your head around. And
Yeah.
what's even more interesting is that this isn't even the first time Lopez has found something this big. A couple years back, she was on the team that discovered the giant arc, which is another one of these ultra large structures, and that one's like 3.3 billion light years across.
Wait, so there are two of these massive structures,
Right.
and they're both in the same, like, cosmic neighborhood? What are the chances?
Right. It's wild. They're both visible from Earth, same redshift, which means they were around at the same time in the universe's history. And get this, they're separated by only 12 degrees in the sky. I mean, to find two structures this big, so close together, it's really something.
Okay, so they're huge, they're clustered together, but why is that such a big deal? Why are they so problematic, for how we currently think about the universe?
Well, they basically challenge one of the most basic principles in cosmology, something we call the cosmological principle.
The cosmological principle, that's the idea that the universe, when you look at it on a large enough scale, it's, homogeneous and isotropic, meaning it looks the same everywhere, no matter where you are or where you're looking.
Exactly. And this principle, it's been like a guiding principle, for our cosmological models for like decades. But now, with the size and proximity of these structures, and there are others too, like the Sloan Great Wall and the Hercules Corona Borealis Great Wall, well, it seems like maybe this principle isn't completely accurate.
So these massive structures are kind of throwing a wrench into our understanding then. Because the current theories, right, they say that structures can only get to be a certain size, like 1.2 billion light years max. But the Big Ring and the giant arc, they totally blow past that limit.
Exactly. They force us to ask, are these just, flukes, statistical anomalies? Or are they telling us that there's some kind of underlying physics that we don't fully grasp yet?
So are scientists just scratching their heads then?
Yep.
Or are there any ideas out there for how these structures could have actually formed?
There are a few interesting possibilities. Initially, some folks thought the Big Ring might be related to what we call baryonic acoustic oscillations, or BAOs for short.
BAOs, I think I've heard of those, but to be honest, they always kind of made my head spin.
Yeah, they can be a bit mind-bending. Basically, picture the very early universe, right after the Big Bang. You've got these sound waves traveling through this primordial plasma, and as they travel, they create these ripples in the density of matter.
So like ripples on a pond, but on a cosmic scale.
Precisely. Now, as the universe expanded and cooled, these ripples, they became frozen in place, leaving behind this characteristic pattern in how galaxies are distributed.
And we expect these patterns to be spherical, right? Like giant shells of galaxies.
Exactly, spherical. And that's where the problem comes in. When Lopez and her team looked at the Big Ring really closely, they saw that it's way too big and not spherical enough to be a BAO. It looks more like a ring or even a coil, which isn't what BAOs should look like at all.
So we can rule out BAOs then. What else is on the table?
Well, another possibility is something called cosmic strings. Now this is hypothetical, okay? But imagine these incredibly thin, super energetic wrinkles in the fabric of the universe, almost like little defects in space-time.
Wrinkles in the universe.
Yeah.
Okay, now my head's really spinning. But how could those lead to something like the Big Ring?
The idea is that these cosmic strings, which would have formed very early on in the universe, right? They could have acted as like gravitational seeds, attracting matter and energy over billions of years. and then all that matter clumping together, well, that could lead to the formation of these large-scale structures.
So these strings would be like a cosmic scaffolding helping these structures form. It's definitely a fascinating idea.
It is, and it's an area of research that's got a lot of attention. There are some pretty big names in physics, like Jim Peebles, who won the Nobel Prize. He suggested that cosmic strings could explain other weird things we see, in how galaxies are distributed.
Wow, we're getting pretty deep into the weeds here. Are there any even more, I don't know, radical ideas out there?
There is one, and this one comes from another Nobel Prize winner, Sir Roger Penrose. He's got this theory called conformal cyclic cosmology, CCC for short.
CCC. Okay, you got my attention. Tell me more.
So CCC basically says that our universe isn't just a one-time thing. It's part of a cycle, maybe even an infinite cycle of universes. Each cycle, they call it an eon, expands and collapses. And when it collapses, it leaves behind these faint imprints, little echoes, on the next cycle.
So these are like echoes, remnants of previous universes. That's some pretty mind-blowing stuff.
It is, and according to CCC, some of these echoes could show up as rings, like in the cosmic microwave background radiation, the leftover radiation from the Big Bang.
So the rings we see could be signals from a past eon. Wow, that's way different from how we usually think about cosmology.
It is, and yeah, it's still a pretty speculative theory. But discoveries like the Big Ring, they make us think about ideas that, a few years ago we might have thought were completely crazy.
So we've got cosmic strings, echoes from other universes. Is this all just speculation? Or can we actually test these theories?
That's the exciting part. Lopez and her team, they didn't just stumble upon this Big Ring by accident. They used a very specific technique, they call it MGII absorption systems, to find it.
MGII absorption systems sounds pretty technical. Break that down for me.
Okay, imagine you've got a flashlight and you're shining it through a fog. You wouldn't see the fog directly, right? But you'd see how the light is affected by it. That's basically what they're doing. But instead of a flashlight, they're using the light from incredibly bright, super distant objects called quasars.
So quasars are like their flashlights, and the Big Ring is the fog.
Exactly. The light from these quasars, it travels for billions of light years to reach us. And on its way, it passes through galaxies and clusters of galaxies. And a lot of these galaxies have magnesium gas in them. And this magnesium gas, it absorbs very specific wavelengths of the quasar's light.
Ah, so by looking at the light from the quasar, they can see where this magnesium gas is, even if they can't see the galaxies themselves directly.
That's it. And by analyzing those patterns of absorption, they can basically map out all the matter between us and the quasar, and that's how they found things like the Big Ring.
So they're basically using quasars to, backlight the universe.
That's a great way to put it. And what's even more convincing is that they found evidence to back this up using other data, too.
Wait, so there's even more evidence to support the Big Ring?
Oh, yeah. They looked at data from something called bright field quasars. These are quasars that are in the same area as the Big Ring, but they're not being used as those flashlights for the absorption method, okay? They're just regular quasars in that part of the sky.
Okay, so they're just there. Got it.
Right, and they used an algorithm, a special program basically, that looks for these things called filaments, which are like thread-like structures of galaxies. And guess what? They found a ring-like structure that lines up almost perfectly with the MGII observations.
Wow, so it's not just one method showing this ring. It's like multiple lines of evidence all pointing to the same thing.
Exactly. And there's one more piece to this. They also looked at data from something called the Dark Energy Spectroscopic Survey, or DAS. It's this project that's mapping out galaxy clusters.
So DAS is looking at the, heavy hitters of the universe, these huge clusters of galaxies.
That's right. Clusters, massive concentrations of galaxies, all held together by gravity. And what's interesting is that when they looked at the DAS data, in the same area as the Big Ring, they found some links, we call them intriguing associations, with where those MGII absorbers are. It's like another hint that these things are all connected somehow.
Okay, this is wild. It really is like piecing together a giant cosmic puzzle. But one question I have, if it looks like a ring to us, what does it look like from other angles? I mean, could it be even more complex than we're imagining?
That's where things get even more interesting. Lopez and her team, they used this technique they call the project plane method to see what the structure would look like if we could view it from different parts of the universe.
So they're like taking that 3D distribution of the absorbers and projecting it onto different planes, almost like creating a bunch of cosmic snapshots, each from a different angle.
You got it. And what they found, it really throws a wrench in that BAO explanation. It wasn't a simple ring. It was a coil shape with three distinct bands, each at a different redshift.
Wait, so it's like a giant cosmic slinky?
That's a good way to picture it. And get this, when they looked at it side on, they saw this weird backward S shape and how those absorbers were distributed.
A backward as, okay, now that's a curveball. What could that mean?
We don't know for sure yet, but it suggests it's more dynamic, maybe even rotating, than just a simple ring. And there's one more detail. It has to do with something we call the equivalent widths of the MGII absorbers.
Equivalent widths. That's a mouthful. What does that tell us?
It basically tells us how much light is being absorbed by the magnesium gas.
So a stronger absorption line means more magnesium gas.
Exactly. And what Lopez and her team found is that the absorbers with higher equivalent widths, the ones absorbing more light, they tend to be concentrated in the band of the coil that's at a lower redshift.
So not only is it huge, it's oddly shaped, and now the gas inside it isn't even distributed evenly? What does it all mean? Are we any closer to understanding how something like this could even form?
That's the million-dollar question. And it's probably going to keep cosmologists busy for a long time.
Feels like every time we learn something new, it just brings up like a ton more questions.
Yeah.
But I guess that's kind of the whole point of science, right?
Oh, absolutely. I mean, we're always pushing those boundaries, you know? And discoveries like this big ring, they really show what we can do when we get curious and start getting creative with how we look at things.
This deep dive has definitely given me a lot to think about. I mean, a ring billions of light years across, that makes us rethink like some of the most basic things about the universe, maybe even connected to cosmic strings or echoes from other universes. It's almost too much.
Yeah, it's a lot to process for sure. And I think that's also what makes it so amazing. The universe is huge, complex, and we're really just starting to scratch the surface of what's out there.
And who knows what else is out there waiting for us to find it, right? But let's stick with the big ring for a sec. If we're finding these huge structures more often than we thought, what does that actually mean for, how we understand the universe as a whole?
Well, it means there's still so much we don't know. The Big Ring, it challenges this idea that the universe is all smooth and uniform, especially at those really large scales. It's like it's telling us, hey, there might be stuff going on that we haven't even thought of yet. Stuff that can create these massive, super complex structures.
So it's not just about finding bigger and bigger things. It's about like figuring out the basic rules of how the universe works, how it changes over time.
Exactly. We have to ask ourselves, what are we missing? Do we need to tweak the theories we have? Do we need to come up with something completely new? Those are the kind of questions that really push science forward.
And speaking of pushing things forward, you mentioned Lopez as a PhD student, right? It's pretty incredible that someone so early in their career is making such a big impact.
It really is. Her work shows just how powerful curiosity and dedication can be. I mean, she's using these really advanced techniques, analyzing data from some of the biggest astronomical surveys ever done. She's literally helping to change how we think about cosmology.
It makes you feel good about the future of science. There are so many talented people out there wanting to explore and discover. And with all these new tools, like the SDSS, DSI, and others, who knows what we'll find next?
Oh, I can't wait to see what the next generation of cosmologists will come up with. Every new discovery takes us a step closer to understanding, our place in this incredible universe.
This deep dive has definitely made me see things a bit differently. I mean, the Big Ring is a pretty good reminder that the universe is full of surprises. And our journey to understand it, it's nowhere near finished. But if we zoom out a little, what's the bigger picture here? You said the Big Ring challenges the cosmological principle. But what does that really mean for how we understand the universe?
Well, the cosmological principle, it's been like a fundamental part of modern cosmology. It's this idea that on the grandest scales, the universe looks pretty much the same no matter where you are, no matter which way you look. It helps us simplify things, make calculations, make predictions about how the universe has changed over time.
But now we're finding these giant structures, the Big Ring, the giant arc, that don't seem to fit that idea. So are we saying the cosmological principle is just plain wrong?
It's not that black and white. It's more like we're realizing the universe might be a little more, complicated than we thought. The cosmological principle might still be true, but only on the very, very largest scales. Maybe on smaller scales, things are lumpier, more varied than we expected.
So it's like if you look at something that seems smooth from far away, but up close, you realize it's got all this texture.
Exactly. And that texture, those variations in where matter is, they can tell us so much about, the forces and processes that shape the universe.
So we've got these giant structures, and they're making us rethink some of our basic ideas. But what now? What's next if we want to really understand how something like the Big Ring could form?
Well, the first thing is we need to find more of them. The more ultra-large structures we find, the better we'll understand, how common they are, how they fit into the whole picture of the universe.
And that's where those big surveys like SDSS and DSI come in, right? They're giving us this much bigger, more detailed view of what's out there.
Exactly. And as those surveys keep going, and as we build even bigger and better telescopes, we'll be able to map these structures in much more detail, see their shapes, what they're made of, even how the galaxies inside them are moving.
It sounds like we're entering a whole new era for cosmology. And it's all because of researchers like Lopez who are asking the tough questions and thinking outside the box.
It's amazing to see. Lopez's work is a great example of, what happens when you combine bold thinking with careful research.
So I have definitely got a lot more to think about now. The Big Ring really shows that the universe is full of surprises, and we're still figuring out how it all works. But let's go back to Lopez's work for a minute. You mentioned earlier that she and her team used these bright field quasars to check their findings. Can you explain, how those quasars are different from the ones they used in the absorption method?
Sure. So in the MGII absorption technique, we use quasars as our background light, like a flashlight shining through the gas. But bright field quasars, they're just quasars that happen to be in the same area as the structure we're looking at, but we're not using their light to see anything, they're just there.
So by looking at how these bright field quasars are distributed, they could confirm that ring-like structure, but using a totally different method than the absorption thing.
Exactly. And having that confirmation from a different angle, it's super important because it makes it less likely that what we're seeing is just random, or some kind of error in how we collected the data.
It's like having multiple witnesses backing up the same story. It gives the evidence a lot more weight. And you also talked about DSI, the Dark Energy Spectroscopic Survey, which is mapping all those galaxy clusters. What did they see when they looked at the same region as the Big Ring?
They found some connections, what we call intriguing associations, between the DSI clusters and those MGII absorbers. But it's important to point out that the DSI data is a little bit fuzzier, less precise than the quasar data and those MGII measurements.
So the DI stuff is a little blurry, but it still suggests there's a link between these different structures.
Right, and that's what makes this whole discovery so cool. We've got all this evidence from different sources, different types of observations, and they're all pointing to the same thing. Something really unusual is happening in that part of the universe.
It's like a detective gathering clues, right? Trying to piece together this cosmic mystery. And in this case, the mystery is, how do things as mind-blowingly big as the Big Ring even form?
And that mystery gets even more complicated when you think about that project plane method. When they looked at the Big Ring from different sides, they found this coil shape with those three distinct bands, each at a different redshift. It's not just a simple ring, it's something much weirder.
You mentioned earlier that the middle band that looks like a really thin, flat ring, almost like a pancake, is that flatness? Is that important?
It's definitely interesting. There's been some recent research looking at these flat patterns in cosmic structures, thinking maybe they could be evidence of exotic things like cosmic strings.
Cosmic strings again. It seems like they keep popping up everywhere we look. It's like they're this invisible thread tying all these cosmic mysteries together.
Well, cosmic strings are still very much in the realm of, what if, but the role they could play in creating those large-scale structures, that's something a lot of people are looking into.
So the Big Ring could be another piece of the puzzle, telling us that maybe these cosmic strings actually exist.
It's a possibility we can't rule out. And when you consider that the gas inside the Big Ring isn't evenly spread out, with more gas in the lower redshift band, well, it makes the whole thing even more mysterious.
It's like every time we peel back a layer, there's a whole new set of questions waiting, huh? But that's what makes this discovery so exciting, right? I mean, it's forcing us to think bigger, to expand how we understand the universe.
Exactly. The Big Ring isn't just some weird one-off thing. It's like part of this growing body of evidence telling us that, hey, the universe might be a lot more complex, a lot more varied than we initially thought.
So where does that leave us? If the Big Ring is making us rethink this whole cosmological principle thing, What does that mean for our understanding of, well, everything?
The cosmological principle, it's been so important in developing our models of the universe. It let us simplify things, helped us make calculations, figure out how the universe has evolved over time. But if it turns out that the universe isn't actually as smooth and even as we thought, then those models, well, they might need some work. Maybe we even need to come up with some completely new ideas.
So the Big Ring isn't just challenging one principle, it's maybe challenging, like, the foundation of our understanding of cosmology.
I think it's a little early to say that definitively, but it's definitely pushing us to re-examine some of our basic assumptions.
So what do we do now? What are the next steps in figuring out structures like the Big Ring?
Well, finding more of them would be a good start. The more of these ultra-large structures we can find, the better we'll understand, are they common? How are they spread out? What role do they play in this cosmic web?
And that's where those huge surveys like the SDSS and DSI
Mhm.
come in, right? I mean, they're giving us such a wider, deeper look at the universe.
Exactly. And as those surveys keep going, and as we build new, even more powerful telescopes, we'll be able to study those structures in so much more detail, look at their shapes, figure out what they're made of, even see how the galaxies inside them are moving.
It sounds like we're at the beginning of a really exciting time for cosmology, huh?
Oh, absolutely. And it's all thanks to scientists like Alexia Lopez, who are, pushing the boundaries, trying new things, asking the tough questions.
Yeah, this deep dive has definitely given me a lot to think about. I mean, the Big Ring really shows you that the universe is full of surprises, and we're just starting to uncover them. Makes you wonder, what other mind-blowing structures are out there just waiting to be discovered? What if the way we understand space-time, what if it's way more complex than we ever imagined?
Well, that's the beauty of science, right? There's always more to learn, more to discover. And the universe, well, it's full of mysteries just waiting to be unraveled.
That's a great place to leave it, I think. Thanks for joining us for this deep dive into the Big Ring. It's a discovery that really makes you step back and appreciate just how vast and mysterious the universe really is. And who knows what amazing things we'll find as we continue to explore. Until next time, keep looking up and keep asking those big questions.